Maybe there is one of you who needs an introduction to Eli Porat. So just to be on the safe side, Eli Porat started computer programming and hacking at the age where most children play with marbles and things like that. And he has done lots of work since. He's going to talk now about something he did a year ago, which, as far as I know, is of no immediate application, but you never know with things, and this is very interesting. So, Eli.
Okay. I'm going to talk about range non-overlapping indexing. Okay, next slide. Doesn't move. The bar.
Oh.
Okay. Then I start of the definition of indexing. Given text. The bar. Yeah, okay. It's take time. Given text, I want to pre-process the text, such that given a pattern, I want fast enough to find all the location of the pattern. But in my application, we want to find all the non-overlapping location. For example, here you see that you have here 5 locations of the patterns, but the number of non-overlapping locations are only 3. And I will use this slide to say that the text length is n, the pattern length is m, and oc is the number of occurrence of the pattern. Here we count the number of occurrence of the pattern of non-overlapping. There are some motivation, but most of them only for selling the paper and not actually work. Then let's skip it. What I will show you here is a quick overview on suffix tree. After it, how I'm solving non-overlapping indexing, and after it, how I'm solving range query of non-overlapping indexing. Okay. Then suffix tree. I will start by writing all the suffixes of the text. Here the text is banana. All the suffixes is banana. I add here the $sign. Then it's banana, anana, and so on. And I will start by putting a pass for the word banana. And then adding for it a pass for the word anana, and so on. As you can see here that this subpass used by 2 suffixes, but overall this tree can cost of n squared space. Then we can compress it by, when we add here a pass, a long pass, which was only 1 child to each node, we can compress it by only 1 edge, and this thing will be of n space, and there are several construct algorithms to construct it in of n time. Now, what we are doing with this kind of, with this suffix tree, why we done it, then as you see, each red node here of the $sign is one of the suffix. And now let's seek for the pattern anana. And click. Then the pattern anana, I go in here. I see A and A, and I come here. And now all the red nodes that are in this subtree are the places that the pattern anana is there. Then the time to do it is of m to get on the pass. It takes me of m time, plus oc to get all the leaf in this subtree. It takes of oc time, because to traverse a subtree, which each node have at least 2 child, it takes O of the number of the leaf. The number of inside node is bounded by the number of leaf. Okay. Now I describe what is period and aperiod. Then period sequence is a sequence that repeats itself at least 3 times. Here I I wrote more than twice. For example, AB, 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 it's repeat 3 times. It's have overlap of 3 times. A period string, it's a string that can match, but it can't overlap more than twice. Then this is an example of a period string. Click. Now I will talk about how to do all these things on a period pattern. Then a period pattern, click. We went here on the path, like in the suffix tree, and get here, and now we get here all the leaves here in of leaves time. Click. But we know that the number of occurrence is at least half of the number of the leaves, because it might be the case that there are several overlapping, but there are no more than twice, the number of the leaves can't be more than twice the number of occurrences that we are seeking, because pattern can't overlap itself a lot of time. Then we can actually report all the leaves, and now we need to somehow manage to see which leaf to throw away. To see which leaf to throw away, we actually need to sort this thing and to see which intersects with which. But there is a problem. To sort this thing, it will take of occurrence time log of occurrence, and we want it to take only O of occurrence. Then what we can do, then the solution is renaming. We start by just giving each node here the location in the text. It's take log n bit. Now, in this subtree of size, it doesn't need to be the subtree exactly of the searching as before, but this is subtree is the smallest subtree of size square root of n, of size more than square root of n. I put another ordering, which will cost me. The thing is, I have square root of n element in this subtree. Then to order these leaves, I will use only log of that, and it's half log n bit. And I will do it in recursion here to square root of the fourth root of n. And then I will get, for each leaf, I get a name of log n bit, the order in the string, half log n bit, the order in the area of square root of n of it, 1/4 log n bit, the area in the of the fourth root of n, and so on and so on. All of it is 2n log n bit, and in if we count word is of n space. Okay. Now we have here, we get, let's assume that we get somewhere here. Then we get here to a subtree that have of occurrence leaves. And if I will go backward and will see the renaming for that subtree, I will get a domain of size of occurrence to the power of 2. Now to sort thing in a domain, to sort n variable in domain of n to the power of 2, we can do in bucket sort or something like this, and it will be in linear time. Then we're happy, we can do it in O of occurrence time. Okay? Click. Now, how we deal with periodic string, this is more complicated, but it's nicer. Then the first fact is if we have here a period word, this node is a period word. Now, this period word, it can be the case that the two sons of it are period. Only one of the sons of the period word is period. This AB, 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 B won't be period, but AB, 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 A will be period. It might be the case that it doesn't have any son who is period. It might be the case it will be a son of B, a son of C, a son of D, and so on, and not a son of A. Okay? Then I actually proved to you by fact 1 that that the period pass that we have here, a period pass, that they are not connected. Now I will prove to you that the period paths are really far apart. Why they are far apart? This is the main trick of this algorithm. Then let's start with this A, B, A, B, A, B. This is period. This, let's say that this word is here. Now I want to go to here. This is the next period pass. Then to go to here, then I start by going here. It will be C, A, B, C. But now, in order to get the period pass, I need to do A, B, C, and now again this thing, and a starting of this to get at least 3 times the string. Then it means that if this was size m, this is 2m plus 3, then it means that we double the size of the pattern. But by doubling the size of the pattern, you can see that if I going from a pass from the root to a leaf, it can't be that there are more than log n period passes, because each pass that I get in here, let's say that here was a length 2, then here it must be at least 4, and here it must be at least 8, and so on and so on. It will be that if there are more than log n passes, it need to be more than length n, but we say that the text is length n, then it can be that way, that thing. This is actually the proof that I just tell. Now, what we are doing to a period pass, this I call it a period pass decomposition. What we are doing, we will save a data structure for each such pass. It will be like this. For example, this is the text. I mark here the start of, let's say that this period pass is the period of AB. Then I mark all these places, there are places that the pattern can appear. Then for this string, I mark, click, doesn't work. I start by marking this ABA, which will be for here, because ABA won't match for this pattern, which will be AB. Then for this node, I have a pointer for this record. And from this record, it might be the case that I'm seeking only ABA. I can actually calculate all the non-overlap places inside this or this string. Now, after it, I given a pointer for this this period pass to be able to take all the places that match from here under this pass, because all the places that match here are surely match here. And then after it, for this, I write this sequence. I click, and again, this is I give a pointer to the next period pass. I click, and for this I write this sequence. And now, when I want to query, it's what I'm doing. I'm getting to the node that I want to query. I'm getting to this list. It's here. I calculate how many times it's appear here or where it's appear here, and I can output it. And now I go into here and use this pass data structure in order to find all the locations that in this subtree, and then going back and taking from this all the places that the pattern appear. Okay. Then overall, it's take off and space, because each leaf actually copied only to one period path, and click. And overall, we can see that this algorithm works in of n space of m plus occurrence time for query. Now we are going to deal with range query, which will be more difficult. Okay. Then let's start with the period pass decomposition. What I will do here, another click. As before, I mark here S1, E1, S2, E2, and so on. But now I will put here a number, which this number is the difference between E1 and S1. There is 9 letter years, and here there are 7, and here there are 5. In order to be able to see really fast if a pattern, if I'm looking for AB, 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 which is 6, I know really fast that this thing doesn't contain my pattern. Then if I, for each period pass, if I save this data structure, you can see that now it will cost of n log n time, because each leaf is copied now for each period pass is containing. Before that, we add here a pointer that we use this period pass as well. Now, for each period pass, I have its own data structure, which will be this array. Then the space is of n log n. Now, what we will do with that, this is sorted here by the index, by S1 is less than S2. And actually, you can see easily that E1 is less than S2 as well. And what we will do, we will just, we will get to this node, we will just seek for ij, which we want to find all the occurrence in the text that non-overlap between I to j. And now what we are, this done by of log n time, or another click of log d time. If we are around I, it will take log of the distance between I and where we are. And now what we want to find, for example, here we say that this is AB, 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 which the length is 6. Then we don't want to say this thing, because this thing is less than 6. But we don't want to go over all the places and see that there are a lot of places that they are less than 6. We want somehow to get all the big places before. Then what we are doing what we call range max. There are data structures that report, it's called range max. It reports the maximum given I and j in of one time. And this will report us here this 9, for example. And we know that our pattern 9 is more than 6, and we know that our pattern occurs here, and we can calculate where it occurs. And now we will run it again, range max on this subarray and this subarray, and we report and we will stop only when we get something that less than, in our example 6, less than our pattern length. Then in of 1 per occurrence, we will get a new occurrence. Then overall, it's take for period pattern, it will take of m plus log n plus occurrence. But actually, we will throw up this log n in the next few slides. Now, what we will do for a period? Then the basic thing, what we can do for a period string, we can save, for each node here, we can save a sorted list of all the occurrence of this pattern in the text. But these things can cost, you can click. This thing can cost of n to the power of 2 space. We want it to be less. Then what we will do, we will save only, several places. Another click, another click, another click, another click. we will save these red nodes, which the rule of the red nodes is a node whose size, this node, this is the root of the tree, this have n element underneath it. This node, for example, this will have n over 6, this n over 6, and this 2n over 3. Then we will save only nodes that less than half of the father, less or equal to half of their father. Then, for example, this node we didn't save, and this node as well we didn't save. Okay. Then you can easily see that each red node, each node can have only one blue node. Blue node is a node that we didn't save. And you can easily see that each click. As I said, each red node will keep array of the list of its leaves sorted. And you can easily see by that this thing will cost only O of n log n space, because each node will appear only on log n, at most log n. If a path from the root to a leaf contain only at most log n red nodes, because it always halves the size. Now we add for this here, this blue thing is the list of the nodes that are underneath this node, list of leaves that are underneath of this node, sorted. But now we add here this 3 and 2. We add here for each leaf here, we add when it leaves this blue node. For example, this 5, you see that it's leave after 1, 2, 3 nodes. Then the 5 here have 3, and this leave 7, it's leave after 1, 2 nodes. Then I write here 2. For each leaf here that I store for this red node, I will have a number as well for where the leaf leave this path. Then, as I said before, each leaf copy log n times, and it's of n log n space. Now click. Now what we are doing with that, we have this data structure, and now we query here. It might be the case that here there are 4 and so on, but we query here, and you see this is 1, this is 2, and this is 3. Now, another click. We have this red node with the father of this node. But we don't want to report places that went this way. We want to report places that only beneath these 3. Then it's again, we want to report only things that here more than 3. Then again, we can do for range query, we can find I and j in log n time. I'll click, or log d. And we do again range max. I'll click. And we will get all the places that have here something that are more than 3. Okay. Then it's of 1 per occurrence again. And all of that, and I click. It's of m plus log n plus occurrence. And again, we can reduce this log n. And I click. Okay. Now, how I reduce this log n? I know that is a tiny portion. Then, first of all, if m is greater than log n, we don't need to do nothing. Then we talk about some in a place that m is less than log n. Then for m less than log n, what we will build is a persistent suffix tree. What is a persistent suffix tree? Then first, we will build a suffix tree. This is a suffix tree of the text. Now, we will go over the text, click, from the end to the start. Actually, it can be the opposite. I just choose this way. And now, for each place, I will copy the path of this suffix. I will have another copy of this suffix. Now this copy of the suffix, I will cut it after log n step, because I said that if the pattern is more than log n step, more than size of log n, we actually know what to do. It's we're willing to spare this log n. But if it's less than log n, we want to do something. Then this tree, I know that this path is of log n. Actually, you need for copy a node, you need to copy the pointer for these nodes. Then to copy a pointer for this node, it will cost n sigma log n space, because each node have here sigma pointers. And actually, for binary alphabet, it can be done in of n space. I don't get into details, but it can be reduced, this log n. But now I want to show you how to reduce this sigma, because the thing is that I want to have here a pointer only for things that were before, not things that were after. And then what we will do, we won't save the pointer for the we won't save the pointer outside of this path. We will save it only once in sigma letters. That this will give us the of n space. But now, in order to find, if I'm going now on this path, I want to start from here. This is I, and I will go in this path, and I want to go here. I don't have this pointer. What I will do, I will go sigma copy backs, and in the sigma copy back, I will have at most sigma copy back. I will have a data structure of y fast 3 or some other fast data structure for finding things, and I will ask which is the predecessor of the I position for the letter A or something like this to go to here. And this will cause of log sigma. Then it will take of n log n space, and it will take for each edge going like this, it will take log sigma, then it take m log sigma plus occurrence for query time. I click. Now I want to reduce it, then I reduce it by renaming on each log sigma letter to be one letter, and now it will cost me m log sigma over log sigma, then it will be of m. And actually, to do that, I need to have here a log sigma tree, then it will be this amount of a lot of logs. No, it's log n time log sigma. But actually, it can be reduced as well. Another click?
No, I meant four logs, one after the other.
No, it's log n time log sigma.
I should have booked.
Yeah. Then actually, it can be done in of n log n space. And query, actually, we still have a problem when the pattern is less than log sigma. Then it will be m plus log sigma plus occurrence. Then for summary, we know to do non-overlapping indexing in of n space, of m plus occurrence query time. This trick involved only renaming for sorting the aperiod pattern. We want to sort fast the aperiod pattern and the period path decomposition. And for range non-overlapping indexing, we add of n log n space, of m plus log sigma plus occurrence query time. This involved two tricks. The first trick was with the range maximum. The second trick was with the persistent suffix tree and the renaming. And actually, this didn't involve the renaming thing. But if sigma is small, then actually, if sigma is binary, it will be without this at all. It will be plus n. Then we can do it in of m plus occurrence. Okay, that's all.
When is n smaller than log n?
When is m is smaller than log n? when you are seeking like in the DNA and we want to seek a tiny, tiny thing, like one, how many times one, four nucleotides are decoding things, and how many this portion you have.
So it's smaller than 1, when n is smaller than 1.
When n is really big and m is really small.
No, you said that you care to eliminate log n.
Log n.
When it's bigger than n.
When it's bigger than m.
Another.
Yeah. M is the size of the pattern, n is the size of the text.
Okay,
in most of the cases, this is not the case, for sure. Okay. Okay, and that's all. Yeah.
Do you know approximately what the size of the constants out in front are?
Oh. I can say that they are big because there are ways to reduce, I use in here range maximum and things like this. There are ways to reduce the constants of range maximum. Actually, they are not so big. All the things here are against the worst case. In average case, it can be small. It can be, I don't know, so about 4.
Normal case, they're small enough to be practically useful?
I think that in normal case, you will index all the places and you will sort them, and then you get off the places that you will do things that will take more time, but will be with less bugs. Okay, and that's all.
It's time to speak again.